Hi, I'm Ahmed, and today I'll be giving a sneak peek into our tutorial on model selection for causal effect inference methods. The problem setup that we tackle in this tutorial is the potential outcomes framework. In this framework, we have a set of subjects. Each subject has a feature vector xi, two potential outcomes y1 and y0, and the two potential outcomes correspond to the subject's outcome with and without a certain treatment. And the goal of a causal effect inference method is to estimate the effect of the treatment on each subject. But the problem is that in observational data, we only get to observe either of the two potential outcomes. So a patient is either given a treatment or not given a treatment, but never both. So this makes the problem different from a standard supervised learning problem in the sense that we never observe the true label that we are trying to learn. And to address this problem, a number of methods have been developed over the years. Some methods use ideas from domain adaptation to correct for the selection bias that's induced by the treatment policy in the observational data. Some other methods use ideas from multitask learning using neural network or Gaussian process architectures. And some other methods use generative adversarial networks to estimate the treatment effects. But in real-world scenarios, how do we know which of these methods we should use for the problem at hand? In the supervised learning setup, the answer is very easy. We just use cross-validation. In cross-validation, we have a training sample and a validation sample. The validation sample is not used for training. It's a held-out sample that we use to test the model predictions. And because we observe the labels in supervised learning, we can actually test the model predictions, compare the predictions of the model issue with the actual labels that we observe. And based on the performance of different models on the validation dataset, we can select the best model for the dataset at hand. But we cannot do the same thing for causal effect inference methods. And that's because we never observe the counterfactual outcomes of subjects in the observational dataset. So in this tutorial, we will introduce methods based on plugin estimation to show how we can estimate the performance of a causal effect inference model using observational data. The idea is very simple. We start by imputing the counterfactual outcomes that we don't observe using a plugin model. And this plugin model estimates the treatment effects for each subject in the data and creates synthetic labels for each dataset to convert the problem from a counterfactual inference problem to a supervised learning problem. But of course, because the problem itself is hard, these synthetic labels that we introduce in the dataset are going to be biased. They are not going to be accurate estimates of the true labels. And so we will introduce a technique based on influence function to correct this bias. And having introduced this influence function-based method for model selection for causal effect inference methods, we will show how we can automate the process of modeling choices in causal effect inference problems. That is, we can start with all the different models that exist in the literature and automatically select the best model for each data set at hand and show that this can improve over any single model. Thank you for listening, and please check out the long version of this tutorial on our website.